In the last few lectures, we have been examining the calculation of the effective thermal conductivity of a composite system. Okay. The material consists of a matrix of thermal conductivity Km, okay, in which there are spherical inclusions, spherical particles of a different thermal conductivity K particle. Okay. And across this composite material of length L, there is an applied temperature difference delta T. And what we would like to find out is what is the heat flux. The heat flux of the form the average heat flux. Okay. I will call this direction as the z direction. Okay. The average heat flux Qz is equal to minus an effective conductivity times the applied temperature difference delta T by L, which I will refer to as minus K effective times T prime. Okay, so that is the effective thermal conductivity. And these spherical particles of radius r, okay, with thermal conductivity Kp, which is different from the matrix conductivity. Because the conductivities of the matrix and the particles are different, there is going to be a disturbance to the temperature field. If this were just one material, then the temperature would be a linear function of position. But because there is this difference, the temperature field is going to be different from that linear function. And as I had explained physically, if the particle conductivity is higher than the matrix conductivity, the heat flux lines will pass preferentially through the particles, and the flux through the particles will be on average higher than the flux through the matrix. Vice versa, if the matrix conductivity is larger than the particle conductivity, heat flux lines will preferentially pass around the particle, and the conductivity of the and the flux through the particles is going to be lower than the flux through the matrix. And that is what we are trying to find out in this class. So, first things first, we consider a particle that is placed in a temperature field that is a linear function in the limit of a large distance from the particle. So, I have a plot here the temperature versus this distance, okay, this distance z from the particle center. Far away from the particle, it is a linear function. Because we are considering this in the dilute or non-interacting limit, where the temperature disturbance around one particle does not affect the temperature field at another particle. Okay. So, we can consider this as the temperature disturbance individually due to single particles in this matrix. This is valid only when the distance between particles is much larger than the radius of a particle, or if the volume fraction of the particle is small. Okay. So, therefore, the volume fraction is small. Is small. In this limit, this approximation is valid. So, basically we are considering a temperature field. Okay. So, let me expand this a little bit. and far from the particle you have a linear temperature field. Okay. So, this is temperature as a function of this distance z. Okay. So, this is the z axis, temperature as a function of this distance z. Far from the particle is a linear function. So, T can be written as the temperature, T can be written as the temperature of the center of the particle plus T prime times z for r much greater than 1, when the distance from the center, or rather it should be r going to infinity. Okay. Okay. When you go a large distance away from the particle, there is a linear temperature gradient. As you come closer to the particle, there is this disturbance, which is what we are trying to calculate. And I told you that the total flux cannot depend upon the temperature at the center, okay, because if you change the temperature by a constant value, the flux does not change. So, to the temperature field around this particle, if I add a constant temperature, there is no change in the flux, because the flux is related to the gradient of the temperature. Therefore, I can just consider this second part, T is equal to T prime z, as the temperature far from the particle. Okay. So, the equations for the particle in the matrix become del square T particle is equal to 0 and del square T matrix is equal to 0. Okay. Okay. There are no sources and sinks in this problem. Okay. So, del square, the Laplacian of the particle, temperature in the particle is 0, Laplacian of the temperature in the matrix is equal to 0. Boundary conditions at the surface at r is equal to r. The temperatures have to be the same. You cannot have a temperature discontinuity at the surface. So, Tp is equal to Tm. Okay. So, the temperatures are the same and the fluxes perpendicular to the surface has to be the same. If the flux perpendicular to the surface is not the same, there will be a accumulation of heat at a particular at that particular surface. If the flux in is not the same as the flux out, there will be an accumulation or depletion of heat, which cannot happen if you are at steady state. Okay. So, therefore, minus Kp partial Tp by partial r is equal to minus Km partial Tm by partial r. Okay. So, those are the equations and boundary conditions that have to be solved for this problem. Okay. Spherical coordinate system. In this particular case, okay, I have, okay, this is the z coordinate along the direction of the temperature variation or the heat flux, the average heat flux. Then I have an xy coordinate in the plane x and y. Okay. Any location r, this could be either inside or outside the particle. Okay. Has a distance r from the center of the particle in a spherical coordinate system. The azimuthal angle with the z direction is theta, and the angle made by the projection with the x direction is the meridional angle phi. As you can see, in this particular case, z is equal to r cos theta. The temperature field, applied temperature field, depends only upon z, which depends only upon r and theta. Therefore, there is no dependence in the boundary conditions on the phi coordinates. Okay, which means that the problem is axisymmetric. The temperature field is independent of phi. Okay, the temperature field is independent of phi. Problem is axisymmetric, and the equation in both the matrix and the particle is one by r square sine theta. This is equal to 0. Okay. So, that is the equation for the temperature field in the particle and the matrix. This equation we had solved by separation of variables. T is equal to f of r g of theta. Okay. Substitute into the equation, divide throughout by f and g, and multiply by r square to get d by dr of r square is equal to 0. Okay. Substitute t is equal to f times g in the equation, divide throughout by f times g, and in this particular case you have to also multiply throughout by r square, so that the second term becomes independent of r. Okay. Now, first term on the left is only a function of r, second term on the left is only a function of theta, therefore both have to be constants of equal magnitude and opposite sign. In this case, the inhomogeneous boundary condition is the applied temperature field in the limit as r goes to infinity. In the theta direction, theta goes from 0 to pi. Okay, theta is equal to 0 is the plus z axis, theta is equal to pi is the minus z axis. At both these boundaries, at both the limits of the interval of theta, there are no physical boundaries, therefore the boundary conditions have to come from symmetry conditions. In any case, those have to be homogeneous because the driving is coming in from the r direction in the limit as r goes to infinity. Okay, so I showed you how to transform this. We transform cos theta is equal to psi, okay, and d psi is equal to minus sin theta d theta. Okay. The equation becomes partial, or in this case it is a total derivative because g depends only upon psi, d by d psi of 1 minus psi square dg by d psi, okay, is equal to a negative constant. So, okay, is equal to minus alpha, okay, a negative constant because when you have homogeneous boundary conditions, the eigenvalue becomes, okay, on the right side becomes negative, okay, and so this is equivalent to 1 by g sin theta d by d theta of sin theta dg by d theta. So, I said this has to be equal to minus alpha, okay, and then you substitute g is equal to cos theta is equal to psi and d psi is minus sin theta d theta, and you get this equation in terms of psi. And I had shown you by a series solution in the last lecture that this function g is finite at theta is equal to 0 or pi, okay. Cos theta is equal to 0 or 1, or when theta is equal to 0 or pi. This function is finite only if alpha is equal to n into n plus 1, where n is an integer. Okay. The solution of this equation, you have to multiply throughout, so you will get d by d psi of 1 minus psi square dg by d psi plus alpha g, this is equal to 0. The solutions of this second order differential equation are finite at g is equal to plus or minus 1, at psi is equal to plus or minus 1, only if this alpha is equal to n into n plus 1 g, where n is an integer, okay. And then the solution for g is equal to p n of cos theta, okay. So, this is called the Legendre equation, and this is called the Legendre polynomial. Okay, p n of cos theta, okay, which is the same as of psi. Okay. and I had listed out some properties of these. Pn of psi, okay, is polynomial of order psi, sorry, n, okay, contains alternate powers, that is, okay, okay, or let me be more specific, contains only odd powers of psi for odd n and even powers of psi for even n. Okay. So, it is a Legendre polynomial, it contains only odd powers of psi for odd n. Note that psi varies from -1 to +1, because cos theta is equal to 0 implies psi is equal to +1, sorry, theta is equal to 0, cos theta is +1, theta is equal to pi, cos theta is equal to -1. Okay. So, the range of psi is between -1 and +1. Therefore, if n is odd, it is an odd function of psi, okay, it contains only odd powers of psi, and n is even, it contains even powers of psi. Normalized so that, okay, the modulus of Pn at plus or minus 1, this is equal to 1. Okay. So, Pn, if n is even, then Pn of plus 1 is 1, Pn of minus 1 is 1. If n is odd, Pn of plus 1 is 1 and Pn of minus 1 is minus 1, okay, because odd function Pn of minus psi is minus Pn of psi, and even function Pn of minus psi is plus Pn of psi. Okay. And the orthogonality relation is integral d psi between minus 1 to 1 Pn of psi Pm of psi is equal to 2 delta Mn by 2n plus 1. Okay. So, these form an orthogonal basis set. Okay. These form an orthogonal basis set similar to the sine and cosine functions, the Legendre polynomials that we had, except that this is now defined for psi going from -1 to +1 or for theta going from 0 to pi. In this case, the integral will be sin theta d theta Pn of cos theta Pm of cos theta. Okay, this is equal to the same thing, okay, 2 delta Mn by 2n plus 1. So, that was one part, we solved for the g part. The second part was for the radial contribution. Okay. So, the radial contribution we have 1 over f d by dr of r square df by dr is equal to, in the case of g we had minus n into n plus 1, in this case we have plus n into n plus 1, and I had solved it in the last lecture for you to get f is equal to a by r power n, sorry, r power n plus b by r power n plus 1. Therefore, the solution for the temperature field is equal to a r power n plus b by r power n plus 1 p n of cos theta. Okay. This is a solution that satisfies the equation and it satisfies the boundary condition in the theta direction, because we had homogeneous boundary conditions in the theta direction for any value of n. Okay, this satisfies the equation and it satisfies the boundary condition in the theta direction for any value of n. That means that the most general solution is a summation, okay, to infinity of a n r power n plus b n by r power n plus 1. Okay, so, that is the equation and the that is the solution, and of course, a n and Bn have to be determined from the boundary conditions in the radial direction, because that is what we have not yet enforced so far. Okay. So, for example, I also gave you the first few Legendre polynomials. This is one, P1 of cos theta is equal to cos theta, P2 of cos theta is equal to 3 cos square theta minus 1 by 2. Okay. So, now the coefficients a n and b n have to be determined from the boundary conditions. What were the boundary conditions? Okay. At r is equal to r, right, Tp is equal to Tm, okay, and minus Kp partial Tp by partial r is equal to minus Km partial Tm by partial r. Okay. So, this solution, as I said, is valid both within the particle and the outside the particle. So, I can have within the particle, I can have sigma n is equal to 0 to infinity. Okay. A particle n r power n plus b particle n by r power n plus 1 p n of cos theta. Okay. T matrix is equal to summation n is equal to 0 to infinity A matrix n. I should, okay, so let me use other symbols here. So, I will call this as okay, so these are the solutions. Boundary conditions T particle is equal to T matrix minus K particle, T particle by Tr is minus K matrix, T matrix by Tr. Okay. And also I have a condition as r goes to infinity, the temperature in the matrix is equal to T prime times Z, okay, which is equal to T prime r cos theta. Z is r cos theta, and cos theta is the same as P1 of cos theta, okay, is equal to T prime r P1 of cos theta. Okay. Okay. So, the solution for the temperature field consists of a summation over all Pn. Okay. At the particle and the matrix, the interface between the particle and the matrix, you have equality of temperature and equality of flux. In the limit as r goes to infinity, when I express the solution in terms of the Legendre polynomials, I get something that goes as T prime r P1 of cos theta. Okay. So, if I expand out this as summation over n of sum, okay, Cn r power n, okay, times, okay. So, yeah, let me first discuss these two terms. Okay. The first term here is what is called the growing harmonic. It increases as r increases. Okay. The growing harmonic increases as r increases. It goes to infinity as r goes to infinity, and it is 0 at the origin. This is what is called the decaying harmonic. This decreases as r increases. Okay. This decreases as r increases, it is infinite at the origin and it goes to 0 as r goes to infinity. Okay. And these are the Legendre polynomials, okay, which form an orthogonal function set. Okay. Now, for the particle, right, obviously the temperature has to be finite at the origin. Okay. The temperature has to be finite at the origin for the particle phase. Okay. So, obviously this term in the particle has to go to 0. Okay. In the particle, the decaying harmonics have to go to 0 because they are infinite at the origin. Therefore, their coefficient has to be 0. What about in the matrix? Okay. In the limit as r goes to infinity, okay. Okay. In the limit as r goes to infinity, t prime r p1 of cos theta. Okay. So, therefore, in this series expansion in the limit as r goes to infinity, there is only one term that survives in the limit as r goes to infinity, and that is a n for n is equal to 1. Okay. In the limit as r goes to infinity, the temperature is proportional to p1 times cos theta. So, basically you have a forcing that is proportional to p1 of cos theta as r goes to infinity. Okay. The temperature field is finite at the origin, and you have homogeneous boundary conditions at the particle interface, that is the particle temperature is the matrix temperature and the flux in the particle and matrix are equal. Okay. The only inhomogeneous term is the temperature as r goes to infinity, okay, that is t prime p1 of cos theta. Okay. Because the Legendre polynomials are all orthogonal to each other, right, that means that the only solution is the solution for p1. Okay. So, let us take for example for okay, the case where for n is not equal to 1. Okay. If you are considering the case where n is not equal to 1, then as r goes to infinity, okay, T m. Okay. So, if I just formally write this as the matrix temperature is equal to summation n is equal to 0 to infinity, okay, of C n P n of cos theta for r going to infinity. Okay. For r going to infinity, if I write this, okay, as C n times P n of cos theta, then because this is equal to t prime r cos theta, that implies, okay, because it is proportional to t prime of cos theta, that implies that C 0 is equal to 0, C 1 is equal to t prime, I should write this as r power n. Okay. Okay. C 2 is equal to 0, etc., C n is equal to 0. Okay. The forcing is only through the P1 term here. Okay. Forcing is only through this term, C 0 is 0, C 2 is 0, etc., right. Because these coefficients are all 0 as r goes to infinity, and because I have equality of temperature and flux at the interface, that implies that all the terms in this series are 0 except for, okay, except for n is equal to 1. Okay. So, basically the temperature field I can describe it as an expansion, okay, and at each order in n I can solve it individually, okay, because the Legendre polynomials are all orthogonal. Okay. So, for example, I can multiply this temperature equation T p by P m of cos theta and integrate, okay, and the solution I will get, for example, will be, okay, integral d sin theta d theta times T m of, okay, is equal to integral sin theta d theta into a n m by into r power n plus B n m by r power n plus 1, okay, P n of cos theta into P m of cos theta. Okay. And these are orthogonal. So, on the right hand side, right hand side I will have a non-zero term only for n is equal to m. So, this will just be equal to A m matrix r power m plus B m matrix by r power m plus 1, okay, into 2 by 2 m plus 1. Okay. And so, I have to do the same thing for these equations, okay, for these equations, the temperature in the particle and the temperature in the matrix. Okay. I will continue this in the next lecture to show you what you get when you do these orthogonality relations. So, I will continue this in the next class. I will see you then.